So, good afternoon, everyone. Welcome to the live session. It is the week 8th today. So, we are taking the live sessions on design of steel structures. I'm your TA Danish Bashir from IIT Madras. So, in last class, we saw last couple of sessions, we saw compression members and their design as well, uh, where we solved some design problems also regarding compression members. Now, there was one topic which was left in bolted connections. I missed that topic when we were taking the sessions on the bolted connections. Either it was that butt joint or that lap joint. There we saw design of those connections as well. But we skipped one class that is regarding the eccentric connections. So in today's class, I will be talking about eccentric connections. So what is actually eccentric connection? For example, we have a if we consider one eccentric connection like this, we have a column section like this. It is connected on both sides like this, and on this side as well this. So if it is having a connection like this, some beam is attached to it in this manner, or some plate is attached to this in this manner, and some load is acting on it at some eccentricity from the central axis of this column. Let the eccentricity be E, and this connection may be either welded, it can be welded on two sides, or it may be bolted, like it may have bolts like this. Okay, maybe bolted connection like this. Okay, so when we are having connections like this, the load is not acting through the axis of the member, but it is rather acting at some eccentricity from the joint, or the load is not being load is being transferred through the joint, but along with some eccentricity, which we call such type of connections as eccentric connections. And the design of these eccentric connections is totally different as we considered the connections without any eccentricity. So that the formulas in that were pretty simpler as well. But if we see in eccentric connections, we will see on each bolt there will be some additional moment that will be P times E divided by some factor K, that this additional moment will be acting on our each bolt, apart from the other other forces like shearing force and bearing force on our bolts. So we have to keep in consideration this moment also during the design process. So first of all, I would like to give a brief analysis con analysis concept of this eccentric connections. Then we will solve one design problem also. Okay. So one assumption that I'm making here is that load is lying in the plane of a boulder joint. Okay. So I will write the assumption here. Assumption is that load is lying in the plane of bolted joint. Okay. So it is important to assume here that load is lying in the plane of the bolted joint, because if we consider the out of plane loading as well, first it is with some eccentricity and then it is out of plane, then there will be one more additional moment due to the out of plane eccentricity. So the calculation will become very complex. So that's why we are not considering that case here. So first assumption is load is acting uh, in the plane of the bolted joint. Okay, and one more thing is there. I will make a clear diagram here. So the diagram, our diagram says like this. If this is our column section, okay, I am making these waves on the two sides to make sure that the column is connected continuous on other sides. Okay, and this is one more plate attached to it, or it may not be the plate, it may be any other beam section attached to it. Okay, whatever you can consider there. Okay, so it is like this. Okay, and load is acting like here, it is acting P, load P is acting here. Okay, and we are having the central axis of this column like this. Okay, I will draw one central axis, should be exactly in the middle, huh? So this is the central axis of our section. So there was no issue if the load was acting through this axis, there would have been zero eccentricity. But since the load is not acting through this axis, so there is some eccentricity in our connection. Okay, now this is the eccentricity that is there. Eccentricity is there. So the total moment, one second, I will add this thing here. So the total moment that is acting on our joint like this, I made the arrows in the wrong direction, so it will be turning it like this. Okay, moment M will be equal to P times E. It's the gross moment acting on this. And let us say there are one more thing, one second, one more axis we have to draw in the horizontal direction. Okay, horizontal direction like this. Okay, so let's assume there are 6 bolts given there. Okay, it is given 6 bolts, 1, 2, 3, 4, 5, 6 bolts are there. Okay, so I am writing here for your convenience that P direct load. Okay, direct load. Okay, it is there. Bending moment, PE is bending moment. Okay, what else is there? So direct actual shear on each. Uh, so I am assuming that n number of bolts in joint. Okay, so how therefore direct axial shear on each bolt bolt, that is PA will be equal to total load P divided by N. Okay. I already told where PA is actual load. Let us assume FA force on each bolt due to actual load. Okay. Sorry. Let's assume force on each bolt due to actual load. Okay. Okay. So I am taking this section. Okay. I am taking this section here. I am redrawing it again. Okay. Let me take this, and I am, since there are six bolts like this, one, two, sorry, bolt is in the circular shape, two, what's happening, two and three. Okay, so there we are having these six. Okay, and we need to take this also. This axis we have to put it here. Okay, so this is the our enlarged view of our bolts. Okay, so there will be one more force on these bolts, one more force on these bolts. I am telling you, there will be one more force on bolts, that is Fm. What is this? This is a shear due to moment. Okay, due to moment on each bolt. And the nature of this shear force on each bolt is such that acts tangentially and is perpendicular to radial direction. Okay, so if I consider, I am taking two colors here. This color I am using for axial shear. Okay, so axial shear on each force will be in the downward direction as the load is acting in the downward direction. Okay, so axial shear will be equal. Are you getting my point? Okay, axial shear FA, FA, FA. Okay, FA, 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 axial shear, and I am denoting by violet color. I am denoting shear due to moment. Okay, so I told you in each radial direction it will be perpendicular. So the radial direction is this. For this one, for this it is, this is the radial direction, and for this is the radial direction, and for this is the radial direction. Sorry, I'm making little bit enlarged for this people. And for this is a radial direction, and the shear force will be perpendicular. So the perpendicular thing I am making like this. I have to make it such that it is perpendicular. So this is Fm, and that direction of that perpendicular is such that it is following the moment. Okay, since our moment is in this direction. Okay, our moment is in this direction. So if you are seeing that I am making these forces in that direction also. Okay, uh, this is Fm here, Fm here, and this will be Fm here also. I hope you guys are following me. Okay, okay, let's take 5 minutes break. So it acts, we are back. So it acts perpendicular to the radial direction, and the sense of this force is in such a way that uh, it is in the direction of the moment. So this shear force Fm has a proportionality with the radial distance from the center of the joint. Fm is directly proportional to R. This is assumed in the design process, and then this that Fm be equal to Kr, where K is a constant. Okay, constant. Okay, this is there. So the total moment on the joint MT will be the summation of all the moments on the each bolt. So Fm, and the distance of each bolt from the center is R, radial distance R, Fm into R. So Fm is actually equal to Kr. So it will be K is constant. It will be K is equal to summation R square. Okay, or we will get the value of Mt to be equal to K is actually equal to Fm by R. Okay, Fm by R summation R square. Okay, I hope you guys are following me. Summation R square, or Fm shear force on each bolt will be equal to Mt into R, Mt into R divided by summation R square. Okay, but we know that Mt total moment on the joint is equal to P dot E, P into E. So shear force on each joint Fm will be equal to Pe into R divided by summation R square. So this is Fm force on each bolt. Okay, then moving forward. So if I draw the one bolt here, and it is having some radial direction like this with the joint center R, this is the joint center R. So it will be having FA like this. It will be having FA like this, and it will be having, let's take example, it will be having FM like this. Okay, FM like this. Okay, then there is a, and theta is the angle between these two. Theta. So there will be one resultant force acting on this bolt. There will be one resultant force. This is theta. There will be one resultant force acting on this. It will be Fr. Okay, this is theta. So this Fr resultant force Fr will be equal to summation of, not square root of, Fm square, two vectors vector addition, Fa square plus twice Fm Fa cos theta. Okay, this is the resultant force acting on one bolt. Okay, so I hope this thing is clear to you guys. We will solve one design problem on it. Okay, so let's consider this problem. Now let's make new one. So problem first of today's session. Okay, So problem first of today's session is we are having a column like this. Okay. Okay. We are having this section attached to this, and the central line is this. Another central line is this. Sorry. We have to make them dashed. Okay. We have to make them dashed like this. Okay. It is having 6 bolts. Okay. One bolt is here. 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 Okay. So the end distance. Sorry. So the end distance this is given as 40 mm. All the dimensions are in mm. Okay. 40 mm, and this pitch gauge is given as 60 mm. Okay. 60, and this is again and as 40. Okay. 40 mm. The eccentricity of the load is 180 mm. Okay. So they are saying that some load P is acting on it, and this is a 12 mm plate joined to it, and this is ISWB 350 section. Okay. 350 section, and the bolts are high strength friction grip bolts. Okay, of grade 8.8 grade with 20 mm diameter. Okay, you people note all these details, these are in the questions. And the slip factor for HF HSFG we have to take as 0.5. Okay, this bracket plate is 12 mm thick. I already told you this bracket plate is 12 mm thick. So we have to calculate this P that can be safely transmitted by this bolted connection. Okay, so let us start this problem. Proof load of, first we will calculate the proof load of HFSG bolt. Okay, load of HSFG. Okay, so F naught we know that A and B times 0.7 times bearing strength of the bolt. A and B is 78%, 0.78% of the gross area. That is pi by 4 into 20 square is the diameter into 0.7 FB. We have to take 800 because these are 8 grade bolts. So FB will be FNB actually. FNB will be 800 megapascal. Okay, this is 137 kilonewton coming out. Okay, now the first thing we have to calculate is the slip resistance. Slip resistance. So slip resistance VDSF of the high strength friction grip bolt is given as mu F times Ne times Kh divided into proof flow divided by gamma mf. Okay, so the values of the different things are 0.5. We will take Ne is 1 and Kh factor we will take 1 and F naught we calculated 137 divided by we will take gamma mf to be 1.25. I am assuming all the things. Assume gamma mf F to be equal to 1.25 and E to be equal to 1 and Kh I am assuming all these factors to be equal to 1. It comes out to be 55 kilonewton. Okay, so second is we have to calculate strength in bearing because we have to calculate the bolt value. Okay, so strength in bearing VDPB of bolt is given as 2.5 kb factor times D times T times Fu divided by gamma MB. Okay, now the kb is a factor which is actually equal to the least of these two quantities, that is and edge distance divided by 3 times total gross diameter, that is equal to 40 and distance is 40. Okay, and distance is 40. 40 divided by 3 times 22, gross diameter is 22. We are giving a diameter of 20 mm and taking clearance of 1 mm on each side, so we get the gross diameter as 22.5. Okay, D naught. Okay, it comes out to be 0.606, or we have to take P divided by 3D naught minus 0.25, where P is the pitch. Okay, pitch is 60. Okay, 60 divided by 3 times 22 minus 0.25 comes out to be 0.66. So we are taking this value, least value. Okay, 0.606. So our KB comes out to be 0.606. Okay, uh, okay. Then VDPB comes out to be 2.5 times 0.606 times D is 20 times thickness is 11.4 times FU is 410 divided by gamma MB is 1.25 gamma FF and gamma MB I am taking gamma MB to be equal to 1.25, so it is equal to 113 kilonewton. So bolt value will be the least of 55 kilonewton or 113 kilonewton, either in slip resistance, minimum of slip resistance and minimum of bearing. So bolt value will be equal to minimum of the two. So bolt value comes out to be 55 kilonewton. Okay, now I will take this one bolt because all these bolts are symmetric. This are symmetric. These are four common. These two are different. So R will be same for these four and R will be same for this. So if I take like this is the central line. Okay, this bolt is at this distance. So this bolt is at this distance. So for this gauge pitch distance is 50 and this gauge distance is 40. Okay, and this is 60 actually. You can see that actually this distance is 50. Okay, 50, and this distance is 60. Okay, this distance. So this r comes out to be, this r comes out to be root under 50 square plus 60 square. Okay, that comes out to be 78.1. And for another bolt, which is on the axis like this, r comes out to be, this is r1, r2 comes out to be 50 directly. So summation of r square comes out to be, so we have 4 bolts, 1 2 3, these 4 bolts, sorry, these 4 bolts and these 2 bolts. These 2 bolts. So we have summation of r square comes out to be 4r1 square plus 2r2 square. If I put all the values, summation of square r square comes out to be 29398 mm square. Okay, also the actual force on each bolt is p by 6 because bolt number is 6. So fm1 shear force due to moment on bolt type 1, this is bolt type 1, bolt type 1, bolt type 1, bolt type 1, this is bolt type 2, bolt type 2. fm1 will be equal to p e r1 by summation r square. Okay, so this will be p into 180 into r1 is 50, this is not this 50, this is 78.1 divided by 29398 because we calculated this r square value. So fm1 comes out to be 0.478 p. Similarly, if we calculate fm2, it will be p into 180 into r value is 50 divided by summation r square, it comes out to be 0.306 p. So we got fa and fm also. Okay, so the resultant on bolt type 1 and bolt type 2 will be fr1 resultant will be summation fm1 square plus fm fa square plus twice fm fa cos theta. So the value of the theta on this bolt is actually, this is in this direction, fa, and fm is in this direction. Okay, fm, so this is theta between them. Okay, actually this will be theta also. Okay, so theta will be, tan theta will be equal to, actually it will be equal to 60 by 50. Okay, or theta will be equal to tan inverse 60 by 50. I hope you guys are following me. Okay, so I will get fr1 if I plug in all the values of theta and all. I will get r1 fr1 equal to 0.599 p, and similarly fr2 I will get, since there is no angle between the forces, it will be equal to fa plus fm2. This is fm1, this is fa. So on this is fa in this direction and fm2 in this direction also. So it will be just the summation, and it comes out to be 0.306 p plus p by 6, it comes out to be 0.437 p. So Total resultant Fr will be equal to max of Fr1 or Fr2. Fr1 comma Fr2. We have to take the maximum for the safe load. Okay. So resultant force Fr we will take 0.599 P on each bolt. Okay. This will be the bolt value. Now this resultant force on each bolt should be at least equal to the bolt value. Okay. So 0.599 P should be equal to bolt value was coming out to be 55 kilonewton. If we solve this equation, we will get the value of P to be equal to 92 kilonewton. So 92 kilonewton is the safe load that can be transmitted by this connection having 6 volts. Okay, safe load transmitted. So in today's section, we saw analysis of this bolted connection, eccentric bolted connection, where I saw you the whole basic theory behind this, and then we saw one design problem wherein we calculated the maximum safe load that can be transmitted by a eccentric bolted joint having 6 volts. So thank you everyone for joining the session. Okay, thank you.